All right, so let's continue. So last time I mentioned that there is one more problem that somehow was not shown in the problem set. So that has been fixed, and it is in the problem set posted in your homework 13, I believe. So anyway, right, the point is, right, for these moment chain functions, what you need to know, right, is the moment chain functions of the well-known random variables, like the normal, the Poisson, the binomial, right? And how to find it, and right, how to find the moments with it, right? Which is the problem demonstrated here. The central limit theorem, right, and the law of large number, while very, very important, will not be a target, okay, for the exam. So the problem that was not there from last time is this one, right? So you're given two, I guess, random variables, right, with their moment sharing functions, and they are assumed to be independent, right? And you ask several questions, okay? And I guess the first one is to find the probability that the sum is equal to 4, equal to 2, right? All right. So what should we do here for part A? How can we find this probability? Well, the answer is, right, that basically you need to recognize, right, that, for example, from this moment sharing function, that what kind of random variable is x? X is a Poisson, right? 2 distribution. Okay. What about y? What random variable is y? Y is a binomial, right? 10 and 3/4, right? Because that's p, right? And then that's 1 minus p. Okay. And so from there, right, of course, the sum equals to 4 is a product, right? Because it's they're independent. E to the minus 2, 2 to the k factorial, right? And then 10 choose 4 minus k, 3/4 to the 4 minus k, and 1/4, right? I guess 10 minus 4 minus k, right? Which is, okay. And then sum k from 0 to 4. Because, right, basically, right, if the Poisson takes on value k, then the binomial, right, takes on the value 4 minus k. Okay. Any question about this? Part B is the same, right? For part B, well, if x times y equal to 0, that must mean, right, one of them is 0. So that's going to be probability, right, x equal to 0, right? This is inclusion, exclusion, right? Either one of them is 0 is enough. And so, right, you just fill in e to the minus 2, and then this is 1/4, right, raised to the 10, and then both of them being 0 is the product. Okay, any
Professor,
question?
for A, why is the bounds of the sum from k equals 0 to 4?
Oh, I for some reason that for obsessed me. Is
Oh,
2.
oh.
Yeah. Thank you for that. Yeah, I did say this is equal to 4 for some reason. Yeah, I that for yeah somehow. Thank you for reminding. Yep, it's a 2. 2. Yep. So this is 2. Yep. Thank you for that. All right. Any other question? Okay. The last one, right? Of course, it's just expectation of x times expectation of y, right? Which is 2 times well np, right? Like that. Okay. So the point is actually ABC are very simple, right? The crux of the problem is recognizing the moment-sharing functions as representing, right, the random variables um, that we want to talk about. Any question? All right. So if not, right, let's move on to our last material uh, for the semester, which is conditional distribution. Right. So this is a logical follow-up to joint distribution. Okay. So in fact, like usually people would talk about conditional distribution right within the joint distribution materials. So this, in a way, belongs to lecture 9. But in some other way, conditional distribution is deeper, all right, than just a formula. And the reason, right, is its connection to the law of total expectation and law of total variance right here. Okay. So this is like, well, from my point of view at least, right, this is the bridge, right? Well, this part right here is the bridge from, let's say, a beginner's class like this to more advanced materials like stochastic processes and other kind of work. Because the whole, I guess, framework of probability sort of relies on conditioning a lot to do work. So to be able to kind of do probability efficiently, whatever that means, conditioning is a crucial topic. Therefore, right, this deserves a treatment in itself and should not belong to the joint distribution. Even though, as you see, the formula easily derives from the joint distribution. The reason, right, is of course, right, conditional is just joint over marginal. So that's the sort of the formula, right? Nothing to talk about really. But if everything ends there, then of course, right? There's nothing to talk about. But it's just a formula. How to interpret the formula, how to use a formula efficiently, and again, right, in the context of this law of total expectation and total variance is where right things shine. Okay, so right, conditional distribution is like conditional probability, if you will, right? But for the random variable version, right? So if you know how two random variables x and y behave together, as in their joint distribution, then it's natural to ask how does one of them behave, knowing, right, or given the value of the other, right? Knowing what the other value is, how does that affect, right, the distribution of the previous one? So that's a general question. Now, the thing, right, again, with conditioning is when you write things down, the symbols might look symmetric, meaning there's no distinction between, right, how important they are, what role they play. In conditioning, right, we emphasize that X and Y do not play the same role and they're not symmetric, right? Y is a fixed value, Y is known, while X there is really a placeholder, right? X is there just to calculate probability. In fact, right, it should be replaced by a dot because we will change X for a fixed value of Y, okay? When we do that, we have a conditional distribution. Okay, any question? Now, so, right, as I said, the formula is straightforward. Conditional is joint over marginal, right? However, the challenge again is in the interpretation, right? Y is supposed to be fixed and the X value is supposed to be changing, which is not really shown, right, in this formula. That's just a definition of how you calculate out. But Y is supposed to be fixed, Y is supposed to be known, X is a changing one. So all in all, right, is the one right here that we look at, right, as a random variable for fixing a Y. So when we sum over all X values, we get 1. So it's a proper PMF, probability mass function, for jointly discrete. Okay. So the one thing we want to pay attention to, of course, is you don't want to condition on the value of little y, right, that is outside the support. And this is again, right, the relevance of support, because if this is equal to 0, then you are dividing by 0, right? So that makes no sense. So basically, you have to condition on, right, event with positive probability. But that said, right, the one thing, right, that goes beyond the formula is the recognition of what this formula is. Okay. So as you see that the problem in the problem set corresponding to this lecture, right, homework 14, basically is all about that, recognizing the well-known distribution when you do conditioning. Okay. When you observe the structure here. But otherwise, right, the only thing to pay attention to is not to divide by 0. And there is, right, another step where, right, we abstract away from X to look at a general random variable, right, of X given a particular value of Y. But then, right, you'll see for other reason, we will even abstract away from Y and just talk about X given Y in general. This has use when we look at the law of total expectation and law of total variance, like this. Okay. In the law of total expectation and law of total variance, you have 2 layers of calculation. The inner layer, which deals with the X, and the outer layer, which deals with the Y. So in the inner layer, you can treat Y as a fixed value, that's fine, which is what you do. But when you move to the outer layer, because you take expectation, you have to treat Y as a random variable. If you fail to do that, you will not recover the original expectation. Okay, so there's a switch of concept here, where you have to generalize or abstractize, if that's even a term, from a particular value that you condition on, little y, to a generic conditioning, as in like you just generically know a value of y, of big Y, but you don't care what that value is. Okay. Well, we'll see more about that in the problem. It'll be more clear, more concrete when we look at that. Okay. Any question about this? All right. So conditional density works in the same way, except, right, instead of doing the probability mass function, you use the joint density, right? So again, conditional is joint over marginal. And here's the thing, right? And here's the thing that you should pay attention to. Even though this formula is very, very, very natural, if you will, right? And you will see that formula anywhere. It hides a very important thing, which is, right, this is the conditional density of x given y equals to little y. All right. What's the big deal about that? The big deal is, of course, because y is continuous, x and y are jointly continuous, then probability of y equals to little y is 0. So here we are looking at conditioning on an event with probability equal to 0, which we explicitly said that you should not do up here. Okay. So at this point, you will say, I'm crazy, right? I just told you something to do, not to do, and then I just did it. So I'm crazy. You shouldn't, right? Listen to a lecture anymore, go home, have fun, right? Well, the distinction is, right, here in the case that I say should not divide by 0, that's a jointly discrete random variable. These have mass function. So you should divide by, right, the value in the support. Similarly, right, here you still stay in the support such that the density is positive, right? However, notice that what you back off here is not a probability, but you back off a density, a conditional density. So in fact, right, this formula is quite sophisticated, if you will, right? It's much more sophisticated than the definition, all right, of conditional probability. In fact, right, in a, let's say, a more semi-advanced class, we would prove this formula, show why it makes sense. Again, in the context of allowing you to say you are conditioning on y equals to a particular value of y, even though knowing, right, that that probability is 0. Now again, right, why is there no conflict, or at least no contradiction? The reason, right, is because these are jointly continuous, right? Like the time of 2 buses, right, arriving at the station. Well, right, when you know the time of the first bus arriving is a definite time. Let's say the first bus arrived at, I don't know, the 16th minute, right? Then that's it. X equals to 16 or Y equals to 16. Condition on that, what is the probability that the other bus arrives in a certain time interval, whatever, right? So knowing a concrete or specific value of a continuous random variable is a fact of life, okay? The only thing is that exactly because it's continuous, then the object you're working with is a conditional density and not a conditional probability or conditional mass function. All right. So that's all there is. I mean, not that that's all there is, but that's sort of like the magic about it, if you want to call it magic. If you don't, worry about too much of this, you're happy with conditional density, blah, 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 then, the formula, right, is enough to serve you. All right, any question? All right. So everything else we said, right, works in the same way, meaning that it's a proper density. If you integrate over the x's for a particular value of y, you get 1, right? The conditional density is a proper density. And then, right, again, we say that you can abstract away from, actually here, right? Exactly this is the point that I just mentioned, that here, right? As you must stay within the support of y to make sure you're dividing by a value when the density is positive, but the probability, right, that y taking on that value is still 0. Okay, and that all makes sense because you were talking about conditional density, not conditional probability. Right. Yep. So there you go. Right here, I was saying, right, that basically you cannot, right, apply the definition of conditional probability directly, right, to the case of jointly continuous random variables. Again, because you run into the, so notice, right, here's another difference for you. In the case up here, right, this is something non-zero and divide by something 0 maybe, right, if you happen to divide by something like this. But down here, right, what you have is a undeterminate case. So 0 over 0 is not undefined. It could be, but more properly it's indeterminate, meaning you have to do more refined analysis to determine what that is, right? And again, so it turns out that the right concept to deal with, right, this kind of object, right, is conditional density, okay, rather than working directly with conditional probability as a definition. All right. Any question? All right. So here's an example for you, right? Where, so for the discrete case, right, we'll see the problem set. But for the continuous case, probably the most well-known, right, conditional density formula is the conditional density of the bivariate normal. I mean, you can have multivariate normal, right? And by the way, this actually is linear regression in one variable. You're regressing x on y, right? Notice how this is a linear function in terms of y. Okay, and so yeah, here, right, we're just kind of stating a fact. Well, where do I get this fact from? Well, I got this, if you want to check my work, from this formula, plugging in the joint, right, bivariate normal density that I showed you, right, back in the lecture 9, divide by the marginal of y, which is a normal, you will get a formula that looks like this. I mean, of course, not the normal, but you get the density of this normal, right? So yeah, that is a well-known case, which is saying that if you have a bivariate normal distribution, then conditioning on one variable, the other one still stays normal. And by the way, right, this is actually extremely rare as well, because these x and y are dependent. Okay, so well, I'm not sure, extremely rare, but anyway, right? Yeah, not so sure. I want to say that conditioning it still stays in the same family, but there's some other case I can see that can happen. So I will not gonna generalize that. Okay. You could, right, generalize the whole idea of conditioning to more than one variable, right? So you can talk about the joint distribution of x and y given z. Again, how? Just dividing by whatever, right, that you're conditioning on as a marginal. Then you get the rest, the remaining one. Okay. Well, here comes rather a trivial case, but it's worth mentioning. Remember, right, if two events are independent, then probability of E conditional on F is P of E, right? So we actually took this, right, as the definition of independence back then, right? Saying that basically, independence means that in the knowledge, right, of the event F, then the estimate, right, of the likelihood, the calculation for the likelihood of E does not change, right? So knowing F does not change how you look at the likelihood of E, then E and F are, well, that effectively means, right, E and F are independent. So this kind of idea, right, meaning independence means conditioning has no effect, extends to conditioning too, right? If they're independent, then the conditional PMF is just the PMF, the marginal PMF. The conditional density is just the marginal, right? I actually, again, if you did not recognize this, you apply the formula, you see it right away. But it's special enough, right, to point out. The reason is, it generalizes to conditional expectation, conditional variance, meaning that when you're conditioning, it has no effect. So we just want to highlight that as a special case. Any question? Well, so that's one extreme, right? The first extreme is when conditioning when both variables are independent. The other extreme is conditioning when they are totally dependent. Okay, that's the other extreme, right? Usually you have the case in between where, right, X and Y have some correlation, right? Some connection, some interaction, but not totally like dependent, but also, right, not like independent where there's no interaction. So independent is like no interaction, right? And then totally dependent is like nothing to talk about. Why? Because if they are totally dependent, right, then conditioning doesn't do anything, right? It's either 1 or 0, right? Because basically, if X is a function of Y, right, as a random variable, then knowing Y means that you must know X, period. All right, so nothing to talk about really, right? So again, right, this is a really trivial case anyway, but in symbolic writing, it could come up as strange, as in like, well, we'll point it out, right, when it comes to conditional expectation and conditional variance, right, and in these two special cases. So it's worth just separating them out as special cases. Okay, any question? All right. So now, right, the whole point, or at least one of the reasons why we bother with the notion of conditional distribution is not just to calculate those things out, but to calculate, let's say, objects like conditional expectation and conditional variance, right? And the point, first of all, right, these ideas don't have to be very strange. They are just actually normal extension of whatever you've learned before. Because conditional mass function is a proper mass function. Conditional density is a proper density. So therefore, you just apply the expectation formula to those mass function or to those density, then you get an expectation, right? But instead of calling it an expectation, you call it a conditional expectation because you apply conditional mass function or conditional density function to it. Okay, so nothing strange here should be in terms of concept. Okay, what is really new is what do you do with this? Meaning, why do you care? What's the use? And again, right, I think we kind of give you a sneak peek, right? The use is in the law of total expectation and law of total variance, right? These will help you recover expectation of X and variance of X in some way, right? Yeah. So here, right, we just kind of mentioned the abstract property of conditional expectation. The first thing, right, we should know is that when you take expectation like this, what you have taken out is the X part. You have average out. the x part. So the only thing left is the y part that you conditioned on. That's why conditional expectation of x given y is a function of y. Okay? But if you view this as a generic value, then it's a function of capital Y. You see a difference between these two besides the fact that it sounds like we're just repeating symbols for no reason? Any significance for us to replace little y with big Y? Or, or just like doing it for confusing people. The significance, okay, is that the little y here is a numerical value. So this whole thing is a number. The conditional expectation of x given a y equals to a particular value is a numerical value, is a constant. While here, it is a random variable because big Y is random. A number is very different from a random variable, okay? So as instance, right, 1, 2, 3, 4, 5, 6, right, are numbers or are values that a dice throw can take. But 5 is very different from a random dice toss. You understand? So in this way, it's exactly like this. This is a possible value that this random variable can take. But taking this as a random variable itself is a huge difference. In other words, right, you can take expectation of this guy or variance of this guy, but taking expectation or variance of this guy actually makes no sense or pointless. Okay, so it's not just a symbol swap or just confusing people. These say two very different things. One is a numerical value, and one is a random variable. You understand? Yep. So emphasizing again. So conditional expectation otherwise behave just like expectation, meaning it's linear, right? Regardless of how x and y interacts. Conditional expectation is linear. Right? And this is I guess the gem of this lecture, right? Maybe that when you take the double expectation, right? Some people call this double expectation, law of total expectation. You get the expectation back. Okay. Some example here, but I'll show you one example that's more relevant. So the first thing you should ask, right, is that, well, why do we care, right? Because isn't it easier just to take expectation of x? Why do the whole complex formula? The reason is, again, right, conditioning sometimes is helpful or is meant to make things easy, not harder. Because conditioning, in a way, right, gives you more information or helps you break things down to cases. So x by itself might be hard to control, but when you couple with the information of y, basically, in some way, you kind of break x down to cases or just have some pattern that reviews itself when interact with y. Okay. Well, if you want to put it more bluntly, right, this kind of law of total expectation, or right, is a favorite brain teaser question for interview, right, especially with coding or I don't know, right, finance, that kind of thing. If software engineer is still a thing these days, I have no idea, but right, if you interview for any kind of like sort of brainy job, right, that has to do with something with probability, whatever, then you pretty much guarantee that some question dealing with law of total expectation will pop up. So as a phone interview even. So what is an interesting case, right, for this application of this? An interesting case for the application of this would be back in the geometric example, right? We claim without proof back then that expectation of x is 1 over p, right? I mean, no, we did prove it using the infinite series, right? It's a sum k from 0 to infinity, right? 1 minus p to k minus 1 p, right? K, sorry, right? Actually, we did do this. The trick is with differentiation. So it wasn't that hard, okay? But that's the so-called analytical approach, right? Not a probabilistic approach. And at that time I said, right, the probabilistic approach requires conditioning, which at that stage, we do not have enough tools yet, okay, to talk about. Now we do. So what is conditioning here? What do we condition here? So again, right, expectation of x, the object that we need to find is expectation of x given y. So the key, right, in a lot of these total expectation is to find the appropriate random variable to condition on. You find the right one, the problem becomes very easy. I wouldn't say it's false on your lap, but things show a pattern. You found the wrong thing to condition on, you have nothing, right? Let me just kind of give you an extreme case that it doesn't do anything. The extreme case is you let y equals to x. Well, is the law correct when you choose y equals to x? Yes, it must be. This law is true for every choice. But if you choose y equals to x, then what do you have? Well, the inner one is expectation of x given x, right? Now, what is expectation of x given x? Care to guess? The answer
Just
is
the expectation of x.
nope. That's the wrong guess. That's actually a wrong guess. That will happen when x and y are independent. If x and y are independent, expectation of x given y is expectation of x. But this is not expectation of x.
Oh, is that 1?
Nope. It is x. You think about it, you already know what x is. So expectation of x given x is. It's all right. These are subtle stuff, and that's why I say, right, it's good to highlight. This is the total dependence case, and this is the independence case. When y is independent of x, you have no information. I mean, conditional y gives no extra information. That's why expectation of x given y is just like expectation of x, because you have no extra information. On the other hand, when y equal to x, you have every information possible, right? Again, this sounds mysterious, but think about a dice toss. What is expectation of the dice toss value when I tell you that I just tossed a 3? The answer is 3, right? Because, yeah, right? Understand? What is expectation of a dice toss when I tell you that the GPA of a student in my spring class is 3.0? That information is irrelevant. So the dice toss average is 3.5. Understand? Very subtle. Okay, very, very subtle. Any question? Okay. So here, right, it turns out that the right random variable to condition on for the geometric case is the result of the first trial. Right, remember what does the geometric do? It keeps on, right, waiting until the time, right, for the first success, right, where trials are independent with success probability P, right? So basically, I can condition on the first trial being a success, or I can condition on the first trial being a failure. Now, if I have the first trial being a success, then what does my x look like? which is the total number of trials being to success. What would X look like if my first trial is a success? The answer is, it's just a big fat one, right? Because the first trial is success, so it takes me exactly one trial to get to success. On the other hand, right, if my first trial is a failure, then what? Then basically, right, this IID random variable, right, the nature of independent and identical makes things repeat. And the repetition is as follows. You have one trial, and then you repeat, right, the experiment again. The one, right, represents that first trial that you took, right, that was a failure. Okay.
Professor, are we talking about the expectation here, or like?
We'll talk about the conditional distribution. This notation right here are about conditional distribution. The reason is if I do not know the conditional distribution, forget about taking conditional expectation. Right? If I have no idea what X given Y looks like, how can I take expectation?
Okay.
Right? So now, for example, right, conditional expectation of X given Y equals to 1 is 1. Right? And conditional expectation of X given Y equals to 0 is 1 plus mu X. Well, mu X is this mysterious value I'm looking for. I'm pretending, right? I don't know what that is. Just call it mu X. Okay. Any question? Now, that's the inner layer that I'm working out right here. Now, to do the outer layer, right? The outer layer will be expectation on the Y variable. So the Y variable takes on value 1 and 0, right? With probability P and 1 minus P. So it should not surprise you that expectation of X given Y is P times 1 plus 1 minus P times 1 plus mu X. Okay, that's the outer layer of the expectation. Now, what's the point of all this? Didn't we just create a mess? Well, the answer is no, because we haven't used the law of total expectation yet, right? Yes, it's messy because you're conditioning, right? You're getting more information. But the law of total expectation tells you that in the end, whatever you get must be equal to the true value, which is mu X. So all in all, this approach very often gives you an equation to solve for the unknown, which is the expectation of the variance, whatever. All right. So here, right, to solve for mu X, but notice, right, for example, if you combine this, right, left-hand side, you got P plus 1 minus P, which is 1, right? And then plus 1 minus P times mu X is equal to mu X, right? It should be pretty evident that mu X is 1 over P. Okay, any question? So things like this is what we do a lot in, let's say, stochastic process and whatever, right? That finding the appropriate random variable to condition on and using a lot of expectation, you can simplify the question and recalculate or review the expectation of X, which would otherwise be difficult to calculate. Now again, right, this question, I would say this approach is not that hard as long as you know the right trick. But the geometric is not the hardest thing in the world, right? There are much more harder questions, like finding the number of tosses until you get 2 consecutive heads, head, tail, that kind of thing, right? Those are questions that require like analysis of this type, finding the right random variable to condition on. Okay, but anyway, right? This is just a demonstration of the use of the law of total expectation. Any question? Okay. So yep. So by the way, right, this picture right here doesn't mean much, but basically the law of total expectation from this picture should tell you that it's not really a new phenomenon. It's not that mysterious. Actually, it is really a case of the law of total probability. Or, I mean, it's not a case of, but it operates exactly like the law of total probability. Right? You break things down to cases and then multiply with the probability of those cases happening and sum it up, you should get the original. Okay. And if things are continuous, then instead of doing probability, you do density. Again, in a nutshell, you have to know the right place to put in the formula, right? Okay, so here's a quick proof for those who are interested. So the proof of these things at some point kind of relies on the switching of the order of integration or order of the sum. So notice here we sum over yx, and here we switch over x and y, right? And the reason is when you multiply back to the marginal, the conditional, right, recovers to the joint. And that's exactly the trick to get you to the expectation. Okay. So again, I don't think the proof here reveals too much unless you're already interested in the proof. But it's worth mentioning, right? A lot of this style of like total law of total expectation relies on the switching of the order of integration or switching the order of summation, right? So that basically you recover the marginal, you recover the joint, right, from the product of the conditional with the marginal. So the effect of the outer expectation is it nets you this right here. That's the outer expectation. It nets you this. And the inner expectation gives you the conditional. So these two together gives you the marginal. Sorry, the joint. Okay. All right. You know, the jointly continuous case is the same, right? Notice that instead of a sum, you have an integral. You switch the order of integration, etc., etc. Okay. I don't have time to go into this because it's sort of like a semi-advanced topic, but it's actually very, very important if you guys, any of you, want to do more advanced probability to know this idea. That I think I told you before that independence actually is a very subtle concept. You should distinguish between pairwise independence with mutual independence. Right? First of all, those are not the same thing. Now, you will have the idea of conditional independence versus, let's say, unconditional independence. So you can have random variable x and y that are independent given another random variable z. Meaning if you know z value, then x and y are independent. But surprisingly or not, that doesn't mean x and y themselves are independent. Without knowing z, then x and y could be dependent. In other words, right, long story short, conditional independence and dependence are two different concepts. And you can have examples to show that these are not the same thing, right? So And why do you care about conditional independence? Again, these days, right? As far as I know, a lot of models and whatnot, AI and whatever, does relies on the framework of Bayesian statistics, right? And Bayesian stat is filled, right, with conditioning. So conditional independence is really out there, right, with Bayesian stat and things like that. So that's why you have to know this, because yeah, like I said, conditioning is like the way people do probability, right? But I'm not going to go over this beyond just advertising, right, for its relevance, because like I said, going to this detail is a little bit more advanced at this stage, okay? But it's at the right context. So I just throw it in here, right? If you're interested, you can read the slide or figure out more, right, on your own. But yep, so let's kind of finish this up and then take a break. Conditional variance, right, works in the same way as conditional expectation, right? Just use the right, conditional mass function or the right conditional density. However, right, the key, right, is that the law of total variance here. And notice, right, most people probably know the law of total expectation, but when you ask them to write down the law of total variance, they probably would write down something like this: variance of x equals to variance of x given y. What you see, right, is probably a reasonable generalization of the law of total expectation. But now that you see the right formula, you probably see how ridiculous this guess is. All right. And that's why you need to pay attention and not generalize beyond the context, right? And so is this, right? It has two terms. And actually, right, I think ANOVA is a bit above you guys right now, but analysis of variance or experimental design is a not advanced class in statistics, but kind of like, right, mid forward level or something. You will see this, right, that you have the within group variance and the between group, right? Saying those things is a tongue twister already, right? Between group variation and within group variation, and that's a total variation, right? So you see in ANOVA analysis or experimental design that exactly that within group plus between group gives you the total variance, right? So anyway, I'll just stop there, right? We'll see how this formula comes out when we do the problem set. But needless to say, right, basically variance calculation is always more complex than expectation. That's why the formula is more complex. Okay, any question? All right, so there is no quiz because I stopped assigning homework, so I think it's meaningless to have a quiz. So basically, we'll just take a 10-minute break, right? No quiz, and we'll continue at 7:05. All right, any question? While I have your attention, right, just a small announcement. So basically, the final exam I will not post the solution to a final exam. This is the department policy, okay, not my policy. If you want to see the final solution, you can make an appointment at sometime at the beginning of the fall semester, right? I think over Zoom is okay, right? I can meet you on Zoom and I'll show you the final solution, but it will not be posted. All right. Okay, then.
Professor.
Yep.
During last class, did you mention that some content in last class is not in the final exam, or?
The content that's not on there is already on the announcement. The Laplace number and central lithium proof.
Okay, got it. Thanks.
So basically only, yep, this part right here. The rest are fair game. This is not.
Oh, okay.
Okay. Yeah, it's already on the announcement. All right, so let's I guess continue at 7:07. 707 is sounds like an airplane, right? Anyway. so let's take a look at this last problem set. All right, so this corresponds to the homework 14 post, right? And so basically the first few problems, right, 3 to be exact, are about kind of working with conditional probability. I guess the first 2, the last one, the third one is a little bit different, right? But right, the theme is by kind of recognizing, right, the conditional distribution. Again, right, the thing to remember here is that in general, conditional distribution doesn't have to follow any good pattern, right? Like the one we just talked about in the geometric distribution, right? But sometimes they follow some really nice pattern, and that's when you want to pay attention because this pattern can come up in other applications. All right, so here we have 2 independent binomials, right? And the thing to pay attention to is that they have the same success probability P, okay? And we want to look at the conditional distribution of, right, one of them condition on the sum. Okay. So the first one is really just about, right, this. And at first, you just work with a formula, meaning that this is x1 plus x2 equals to n. Okay. So that's by definition. Now the numerator, right, will be easy to find because, right, x1, x2 are independent. So it's going to be, right, n1 choose k, p to the k, 1 minus p, n1 minus k, right? And then n2 choose n minus k, p to the n minus k, 1 minus p to the n2 minus n minus k, right? Divide by what? Well, now what do we know about x1 plus x2? And this is where, right, the previous lecture about the moment-generic functions and how you sum independent random variables matter, right? There was this problem. Right here, right? That asks you to work with those, right? And so item A exactly is what we need for the current problem. And so using that knowledge, right, x1 plus x2 will be a binomial with success probability P and total number of trials n1 plus n2. So that would be all right. Any questions so far? Now, normally, right, this will be all there is-ish. But these kind of problems is special, are special in the sense that there is a pattern to be found. So we need to look at this and we need to simplify, right? Like I said, normally, right, simplification is meaningless. But when simplification is meaningful, meaning there's a pattern to be found in simplification, then we do. So here, right, what simplifications can we do? Well, notice, right, this p to k and p to n minus k exactly is p to n, right? Similarly, 1 minus p to the n1 minus k, exactly, right? n1 plus n2 minus n, right? This is plus k, cancel with a minus k. So that and that cancel with that, right? Leaving us with the combinatorics, okay? And that's it. The combinatorics actually doesn't do anything. Like there's no reason to expand the combinatorics. Okay, so that's kind of it. But we want to go further. We want to recognize what this is. Okay. So is there any well-known distribution that has the mass function like that? The answer is yes. That is the hypergeometric. Right? Remember, out of N1, you choose the first, out of the blue group, you choose K blue. Out of the second group, you choose the remaining red, and this is your sample size. So that's exactly hypergeometric N1. And I think the hypergeometric notation, I think, is big N, big K, right? And little n, I think. So big N is a total number, so it's N1 plus N2. Big K is N1, and little n is little n. Okay. Any question? All right, but right, that is with conditioning on x1 plus x2 equals to little n. Okay. So I will abstract away from that by replacing little n with x1 plus x2. Why? So the y is actually in part B. Part B asked me to calculate conditional expectation here. And notice, right, it didn't say condition x1 plus x2 equals to n. It just said condition on x1 plus x2. Okay. And why is part B that way? Because it prepares for part C, where it asks you to verify the law of total expectation. Do you understand? And so, for example, right, for hypergeometric with these parameters, then the expectation is sample size, right, times success probability, correct? So here, right, in part B, the answer is sample size, but sample size will be this. Okay. So notice, right, the answer is a random variable, not a number, because x1 plus x2 is random. Any question here?
Professor, can you go through how you got the answer again?
Sure. The answer is from the hypergeometric. Remember, right, if you recognize a hypergeometric, then the expectation follows from a formula of the.
Oh.
Yeah. So that's actually your question also highlights the importance of recognizing, right, the pattern, because part B could be asked like this in of itself. But if you don't recognize it hypergeometric, then I would imagine you would labor with a sum and blah, 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 and not going to get anything recognizable, right? And so, yes, this is actually a relevant question. You need to recognize the hypergeometric, then the answer just falls in your lap, so to speak.
Okay.
By that, I mean quoting the formula, right? And I said it's totally legit. And that's exactly because that's exactly the reason why you have to memorize all the important information about the well-known random variables. Okay, right? So now part C asks you to verify the formula. Now, again, right? This has a taste of convincing you that the law of total expectation works. it doesn't have a taste of, okay, this is a good way to find the expectation of x1. Why? Because you already know what expectation of x1 is, right? It's n1 times p, right? If you use this way to find expectation of x1, I would say that's not wrong, but it's just like a lot of work for no reason. So part C here, right, or A, B, C are meant to kind of walk you through a well-known, well-recognized example to convince you, right, of the framework, more or less. But so the expected answer we already know is n1 times p, right? The suspense is whether whatever you worked out here corresponds to that. And well, you see, right, if you take expectation here, so the expectation, right, so expectation of this guy will exactly fall on the x1 plus x2, but expectation x1 plus x2 is n1 plus n2 times p, right? And then of course that is n1p. All right. Any
Professor.
question? Yep.
So, so how should I understand like the conditional in the expectation here, given that like it's just x1 plus x2 and it's not like they're equal to like a specific constant.
Okay, good question. So how you understand it, right, is actually pretty simple. So for example, right, if you understand expectation of x given y equals to y, right? Let's say you say, yeah, I understand what that is, right? So to be even clearer, right? Let's say, I don't know, for some reason, right? Let's say this is a dice toss. And let's say this is your GPA. I have no idea. I mean, suppose somehow they're correlated, right? So you say that if I toss a dice, then somehow I can figure out the conditional expectation of your GPA based on that dice toss for values 1 to 6, right? But then it would make sense to me to say, well, then I could also discuss this, which is what? Which is really this version, but I just do not explicitly say what the value should be. With the understanding, right, that if you supply a value, then you can work out a specific number. So it's really a plugging in, if you will. That's all there is at that level, right? You're just plugging in. So here you plug in n for x1 plus x2, right? You see?
Mm-hmm.
But so why do I have to keep using n? Well, right, really x1 plus x2 can be any value. So I just replace it like that. You understand? But the swapping, right? So in some sense, even at level B, it doesn't really matter if you use a specific value or not. Okay? I would say that that's an okay answer for B, right? It's valid. But imagine how the law of total expectation would operate with this expression in part C. It would be nonsense, right? You understand what I'm trying to say?
Yeah.
So that's the only reason. And that's actually how it really works, that when you take conditional expectation, you really talk about expectation of x given a generic value of y anyway. That equals to y, little y, is really just there to give you some comfort. Another way to say it is, again, right, you would be comfortable talking about dice toss as a random variable versus I have to tell you what that value is. I don't have to tell you, right? I haven't tried the experiment yet. You understand? So I don't have to. I could talk about the abstract random variable, and that's a more powerful concept. Right? I don't have to do a specific case by case. All right. Any other question? All right. So this actually is a well-known example, right? This is basically, well, what do I want to say here? This is a well-known result in Poisson process, where it's ish is a part of some concept called Poisson thinning, or whatever. The whole point is, right, Poisson gives you the model for the number of events that happen. Now you can go further and categorize the events, right? So for example here, the number of the event is like a person visiting a yoga studio, right? That could be a Poisson random variable. But now you further categorize, right? Or you type, right? You turn the events into types, like male or female, right? Of course, you can do as many types as you like, but here it's just two types, male and female, right? And it turns out that the Poisson interacts very well with those kind of like categorization, right? In terms of multinomial setting. So here we'll just do a binomial case, right? But so let's see. But at the heart of it, you can just look at it as a conditional problem, right? So here you condition, right, x1, which is a number of male customer, based on the total number, right, of customers. Well, so again, right, the first thing to do is just to do x1 equals to k, condition x1 plus x2 equals to n, right? And then, right, you just do the formula. Okay. And it follows almost the same pattern as the previous problem, except now we do a Poisson. So the top right is e to the minus lambda 1 to the k over k factorial, e to the minus lambda 2 to the n minus k over n minus k factorial, right? Because they're independent. The denominator, right, uses the result that if you have independent Poissons and you sum them up, then you get a Poisson, right, with the rate being the sum. Right here, right? The second part. Okay. And so the denominator here will be e to the minus lambda 1 plus lambda 2, lambda 1 plus lambda 2 to the n over n factorial. Okay. And now comes the simplification part. Again, like I said, in general, probably not much simplification can happen, but in well-recognized cases, things simplify tremendously, right? So here, for example, the exponentials, right, simplify. The factorial does not simplify, right? But if you bring the n factorial on top, you can recognize that is n choose k, right? And that is definitely a recognition rather than a simplification, right? But n choose k, okay? And what else? Once you have the n choose k, then you kind of suspect that there's some kind of binomial going on. So you're gonna search for something raised to a k power, right? Well, do we have anything raised to a k power? Well, we have lambda 1 to a k, right? But that doesn't look like a p, right? Because p must be between 0 and 1. But of course, you still have the lambda 1 plus lambda 2 raised to n at the bottom. So, right, it turns out that you can do lambda 1 over lambda 1 plus lambda 2 raised to k. Okay, that leaves you with what? That leaves you with lambda 2 raised to n minus k, right? But of course, you still have the lambda 1 plus lambda 2 raised to n left here that you only use the k part. So multiply with, right? Lambda 2 over lambda 1 plus lambda 2 raised to n minus k. Okay. So that's a simplification, or more like a recombination. Because, right, what do we recognize? We recognize that this is exactly a binomial, right, distribution with p, right, the success probability being lambda 1 over lambda 1 plus lambda 2. Okay, any questions so far? And also pay attention to what is conditioned, right? Conditioned on x1 plus x2 equals to n. So that can be replaced, right, with x1 plus x2 right there, right, for future calculation. For example, right, for part B, right, conditional expectation of this will be x1 plus x2 times lambda 1 over lambda 1 plus lambda 2. Correct? For part C, conditional variance will be x1 plus x2 times lambda 1 lambda 2 over lambda 1 plus lambda 2 square. All right, any questions so far? All right, so now with part B, right, we get to verify not only just the law of total expectation, but also a law of total variance. Okay. And so, yes, we need more room. All right. So notice, right, that again, the point is that we do know expectation of x1, right, and variance of x1, that both lambda 1, right? Here, we're not using these formulas to find expectation and variance of x1. We're really checking, right, that the formula works, or convincing ourselves, right, that the formula works. So, well, if you take expectation of this, right, which is that part B, then you see, of course, right, the expectation will be lambda 1 plus lambda 2 times lambda 1 over lambda 1 plus lambda 2, right, which is, of course, lambda 1. So that verifies the expectation. Okay. Now the variance formula is much more complex, right? Well, not much more, but more complex. We need two parts. The first part is the variance of this, and the second part is the expectation of this, right? Variance of conditional expectation and expectation of conditional variance. Right. So variance of this will require us to square this, right? Because that's the constant. And then variance of the sum, right, is the sum of the variance as long as they're independent, which they are. So here, right, we just have lambda 1 plus lambda 2. Okay. The second one is easier, right? Because expectation, then the constant just comes out. So we have lambda 1, lambda 2 times lambda 1 plus lambda 2. Okay. Now, if everything's done correctly, this must simplify to lambda 1. Well, does it? So if you simplify, right, you got lambda 1 square over lambda 1 plus lambda 2 plus lambda 1 lambda 2 over lambda 1 plus lambda 2, right? And if you factor out a lambda 1 on top, you see that they cancel to be lambda 1. Any question here? All right. Okay. So here, This is Poisson thinning proper, but anyway, right? It's basically the counterpart of the other question. The other question, right, basically has two Poisson subsets, if you will, right? The male and the female, right? And then condition on the total, you see that then they act like binomials. Here, right, exactly is where we distinguish them into type. So, let's say that a person, right, an event is male with probability P, right, and female probability 1 minus P. What can we say about the unconditional, right? Or I guess just the distribution of the male part and the female, right? Total number of people, right? So let x1, right, be the number of male, x2 be number of female, right? Then we want to find probability x1 equals to, let's say, m, x2 equals to n. Okay. Now notice that by itself, there's nothing we can do here with this expression. But what we can do, right, is basically do conditioning, because, right, this is equivalent to saying x1 equals to m, x2 equals to n, condition on x1 plus x2 equals to m plus n. Times probability x1 plus x2 equals to m plus n. All right. Why do we condition? We condition, right, because the problem says each person, right, is male with probability P, female probability minus P. So that effectively says if you have a fixed number of group like m plus n, then the male and the female part will act like a binomial. But if you do not have the conditioning, meaning you don't have a fixed total, then these two do not act like binomial. So that's the key here, right? Condition on the total number, then male and female act like binomial. Without conditioning, it won't. Do you understand? Any question about that? That's the key to this problem. Because then, right, the rest are just kind of filling in numbers, because you will figure out that basically, right, this part is just a binomial. So m plus n, choose m, p to the m, 1 minus p to the n. And this part then is going to be a Poisson. So e to minus lambda, lambda to the m plus n over m plus n factorial. Okay. And again, right, there are things to recombine here. The first thing, of course, is m plus n, choose m, right? It's m plus n factorial, right? Which cancel with this. So you have something like 1 over m factorial, right? You have p to the m, right? Which can combine with lambda to the m to give you something like lambda p to the m. Then, right, seems like what you're missing is e to minus lambda p. So let's put it there. The second part, then you have over n factorial from here, right? Because m plus n, choose m is m plus n factorial over m factorial, right? And then n factorial. And then, right, you have the 1 minus p times lambda raised to n power. And then, of course, right, you can fill in the e to minus lambda 1 minus p. And the thing, right, is if you add these two together, you get exactly e to minus lambda. These two pieces together is e minus lambda. So that's the recombining step, right, for this expression. But what do you recognize? Well, you recognize a Poisson M. I mean, not Poisson M, but a Poisson, right, with value M, and a Poisson with value N. Right. So the conclusion is x1 will be Poisson, lambda p. x2 will be Poisson, lambda 1 minus p, and they are independent. So that's Poisson thinning, meaning that if you look at the type, right, of each of the event of the Poisson, then those types also have a Poisson distribution with rate equal to the success rate of that type times the original rate. Okay, any question? Okay, so those are the three, let's say, well-known discrete problems, right, that you must know. The remaining ones are density, right, and conditional density. Okay, and so, for example, right, let's take a look at this. So here, right, is the joint density function, and you're asked to find the conditional density of, right, x given y and y given x, right? So basically here, there's not much to do besides applying the formula that, right, conditional density, let's say x given y, is the joint over the marginal, right? And so you just have to do like work to find the marginal, right, and divide. So nothing, right, really fancy there, right? Basically, you just get some result. Okay. Now, where, right, this problem could be interesting is part B, where you're asked to find the expectation, oh, sorry, the density, right, of the product. Okay. So how do you find the density of the product? Well, right, you either integrate the joint, right? So basically you have to work with probability z less than equal to z, right? You have to work with the CDF, okay? And then you will want to integrate, right, over the region x times y less than equal to z, right, of the joint PDF. Whatever, right? And find that out and differentiate with respect to z. The approach, right, I want to show you here is the so-called conditioning approach. So in some problem, right, instead of work, so you still have to find the CDF of z anyway. That's a must. There's no way you can bypass that. But a place where you have flexibility is where you do the integration. So here you integrate the joint, right, over the appropriate region. But another way you could do is to use conditioning with the conditional density. Now, normally conditional density may not be any easier than integrating the joint. But in this problem, you have worked out part A, where you found the conditional of x and y, right? So you could leverage that if you recognize some pattern. And what pattern can you see? Well, you see that right here. This guy looks very attractive because effectively, what is it? Is an exponential with rate x. So y conditional on x is an exponential with rate x. You see? And so working with conditioning of y given x is pretty easy. And that's going to be the approach here. Again, not a must. Oh, sorry. Here, actually, it turns out I just work with the joint, right? But so yeah, let me show you, right, how to work with the conditioning. So probability x, y less than z is probability. So I want to condition on X. Okay. Times the density of X. Again, you don't have to do this, but okay. And well, if you condition X equals to little x, then this is Y less than Z over X. Okay. Well, what do I gain from this? Like I said, right? Because you know that Y given X is an exponential. So you know what the answer here is. The answer here is 1 minus e to minus z over x times x. Because that's the CDF, right, of an exponential with rate x. And then you multiply with the density, right? But what's the nice thing? The nice thing is when you multiply with x here, then this entire term is independent of x. So it can factor out. And it factors out as 1 minus e to minus z. And of course, right, notice here I don't even care what the density of x looks like because this is 1. So that's the answer. Okay. So actually, right, it's worth walking through this alternative derivation because what I have shown you here is actually the law of total probability, but the PDF version. So what I've shown you, right, at the beginning of this class is the law of total probability discrete version. This is the law of total probability PDF version. And this conditioning technique can be quite useful when you want to kind of work with combination of random variables. All right, any question about this? All right. Oh, yep. Huh, right here. Okay. Uh, okay. I think this probably is the last one. So for this one, right? Again, the point is what? What is interesting about this problem? What is interesting about the problem is this, let's call big fat C right here, right? Which we have encountered before when we look at joint density, right? This is called the undetermined coefficient. And this happens a lot and exactly in this concept, in this context of actually Bayesian statistics like to do this a lot because they like to work with conditional density and things like that. And so you normally think, right, in this kind of question, you have to find C to even start working, right? Because if you don't know the joint PDF, how do you work? The answer is actually you don't. If you want to find the conditional density of Y, this C will cancel out anyway. So that's the nice thing. So if you work with conditional density, then you can tolerate working with a joint PDF without even determining what the integrating constant is, because it will cancel out in the ratio. Okay, so that's the only message that's worth saying about this problem. The rest are just, calculation. Notice, right? The C cancels out. Okay, any question? Yep, that's the last problem, well, of this class. Okay, any remaining question for anything? All right. So if not, then like the exam, right, will start at 6 p.m. on Wednesday, right? And there's no prior meeting, anything like that. You just go straight to the exam, start take it. You have 3 hours, and then you're done. You don't have to think about probability ever again, maybe. Okay. All right. If
Professor.
not, yeah, go ahead.
Uh, this isn't like not a big thing, but like, do you mind if I like eat a little bit during the test? Because I'm taking it at 6 a.m. So,
Uh, so okay, you will have to show the food before, meaning the at the environment check.
oh,
Meaning,
okay.
do not walk to the fridge or disappear, and then somehow I see a food because who knows
Okay,
what you
yeah,
do,
yeah, yeah,
right?
got it.
If the food is there, and let's say, right, let's have a little, right? Don't have like a big meal there, and who knows what's going on there, right? But a snack or a cake or whatever is fine, all right? But it has to be there at the environment check. Okay.
Got it. Uh-huh.
Yep. Anything else? Okay. If not, then have a good rest of the summer and good luck on your final. All right.
Professor, thank you for the course. Yep.
Yep. Thank you for attending.
Yeah, thank you for the course, Professor.
Yep. Thank you. Thank you for attending.